Good morning, good afternoon, and welcome to ARA's Webinar Wednesday program. I'm Jerry DiMaggio. I'm serving as your moderator for today's webinar, which is entitled Missouri's Experience with High Friction Surface Treatments. Next slide, please. I'd like to first go over a couple of housekeeping items with you. If you're having an issue with sound and you're using your computer speakers, please shut off your speakers and dial in using your phone. If you continue to have an audio issue, use the chat button at the top of your screen and send a brief message to the host, and we'll do our best to help you out. Next slide, please. If you have questions, and we encourage you to submit questions during the entire technical program, send your questions to the host and the panelists. Now, I'm going to repeat that because it's important that you send it to both the host and the panelists when you click on the Q&A button. Those questions will be directly addressed by our speaker at the conclusion of today's technical program, which will be at about a quarter of the hour. Next slide, please. Finally, to view today's presentation in full screen mode, at the top of your webinar settings, you see it's highlighted in this slide. Click on the down arrow, highlight View, and then choose Fit the Viewer. Just as a reminder, everyone will receive 1 hour EDH certificate, but in order to receive your certificate, you must attend the full hour of today's program. Now, I'd next like to introduce our presenter for today. Next slide, please. Mr. Jay Bledsoe is a principal engineer in the Transportation and Infrastructure Division of ARA. Holds a BS in Civil Engineering from the University of, Missouri at Columbia. He served the Missouri Department of Transportation for 32 years, and he joined ARA. His specialty areas are asset management, data collection, and integration of that information. It's my pleasure now to introduce my colleague and friend, Jay Bledsoe.
Thanks, Jerry. I appreciate the opportunity to talk to you today about not only high friction surface, but a little bit about safety in general. Safety wasn't a big part of my career until the last 7 or 8 years at MoDOT. But as we started being in the business of supplying more and more information and data to the safety program, it became a kind of a fascination for me, and I hope you'll get something out of the presentation today. We're going to talk first about a little bit of the background of the safety program at MoDOT. Then we're going to talk a little bit about the Highway for Life program, use of high friction surface treatments on Missouri highways. That was started in around 2013. Then we'll look a little deeper at the Missouri investigation on high friction surface treatments that was done a little later in about 2019. And then we'll kind of roll things up at the end to give you a little idea of what we found. When I first joined MoDOT back in the Middle Ages, the safety program was probably about the same it was in a lot of other states. People work generally off known locations, and when I say known, it's locations that people had observed in practice and would try to address on an individual basis. There was a lot of high incident locations looked at, but there's some issues with that. Part of it is a lag of data availability. You know, we're all engineers and we like data, and the more of it, the better, and the more points you can have on a graph, the better off you are. But if you start looking at these locations where you want a 3 to 5 year crash history or something like that, you have a time lag between the time you identify something and you actually go about trying to address it. And the other issue is there's an issue of kind of chasing crashes. Crashes are, in a lot of cases, they're random events. So you may look at something, you have a a high incident, but then you look at it the next year and it's gone. So there was just some freakish thing that happened during that time period that maybe you didn't really have an incident after all. So it makes it a little bit more difficult. So around 2005, MoDOT had a change in management, and they had a little bit of a change in philosophy of what to do with safety. They wanted to look more at a focus on fatalities and not as much on crash frequency. You can have a lot of crashes in certain areas, but they don't result in fatalities. But they really wanted to reduce the fatals. And I think at the time, in 2005, I believe they were setting at about 1,250 a year fatalities on Missouri highways, and they set a goal to reduce that below 1,000. So the first thing they started to look at was, again, it was a little different philosophy. They wanted to start looking at corridor solutions rather than spot locations. And when I say corridor solutions, as I said a while ago, a lot of crashes are random events. You know, you may have a car that runs across the median, hits another car on an interstate, but if you rush out and put up some barrier at that location, what's the odds that that's going to happen at the same place again? The circumstances were just such that happened, but it may not ever happen at that location again. So what they decided to focus on were corridor-wide situations where they put something like a median cable down down the center of every divided highway. They started putting rumble stripes and rumble strips on the sides of the pavements. They went with improved striping, and wherever possible, they did shoulder additions. The median cable was a kind of a big deal because that was something you could do in the course of a year or two with a few contracts. The rumble stripes and shoulders and that kind of thing weren't done as individual projects. They were just improvements that were put in policy and were, when there was a resurfacing project, you upgraded it as much as you could. And I'm not going to say they did it everywhere, every time, because it depended on the situation, right away and whatnot. But wherever you could, you improved them. The location. You can see an example here where they have the median cable. They also have the rumble strip on the shoulder, and they have the wider striping. Now these are relatively low costs, and they have a relatively long life. The cost is on something like a median cable. Once that's in place, you don't have to do anything with it really until it's hit, and then it has to be repaired, of course. But it lasts a fairly long time. And most of the other ones were associated with the pavement life. When you put the new pavement down, an overlay, you put in the rumble stripes, and they pretty much last as long as the overlay that you put down. So as a result, just as an example, I-44 and I-70 through Missouri, east-west routes, longest routes in the state, interstate-wise, we were seeing an average of about 50 fatalities a year from crossover incidents. The year before the implementation, I think there were 49. The fatalities the first year after implementation dropped to 3 on those two routes. For all freeways, crossover fatalities dropped from 60 a year to about 10 during that 9-year period. So quite an improvement using that kind of facilities. Again, the addition of like a 2-foot shoulder and rumble stripes dropped the fatalities on 2-lane undivided roads about 45% and dropped disabling injuries about 25%. Again, a nice reward for your efforts there. And you can see here, these are kind of a graph of the corridor improvements over time. Here was 2005 when they started that program. As I said, they were up around 1,250, and they wanted to get below 1,000. Well, they got below 1,000 pretty quickly with these types of improvements, and continued that trend down through about 2013. And then we had some little fluctuation later on, but they're still not up where they were before the whole program started. So, and I think it was 2013, Missouri was granted a project for the Federal Highways for Life, and that was the use of high friction surface treatments on Missouri highways. Purpose of the Highway for Life programs was to kind of compare your experience using new programs, new products, new innovative ideas to decide if they work, and if they work, are they a best solution based on cost benefit. So in this case, they were comparing the cost of a traditional friction solution like microservicing or, oh gosh, ultra UBOS. I won't even try to say that today. To the high friction surface treatments to see if those were the best solution. For those of you who are not familiar with friction, I threw this one in just to kind of give you an idea of how friction is measured. This is one of ARA's vehicles. In the back of the vehicle, there's a tank of water. The truck pulls a two-wheel trailer. And right here where my cursor is, you can't see it very well, but there's a nozzle. And at a predetermined speed, usually around 40 miles an hour, a metered amount of water is sprayed underneath the tire. Immediately the tire is locked from the braking system, and the torque that is measured on the axle from skidding that tire is measured, and that's converted to a friction number. Low numbers are very low friction, and they go up from there. The more friction you have, the higher the number. Let's put it that way. The project originally consisted of two projects at 4 locations. The first projects were in Cole County. Cole County, this is where Jefferson City, this is the capital of Missouri. The other two were along I-44 in Phelps County, kind of in the south central part of the state. The Cole County projects, there were 2 locations. The first one was a kind of a sweeping curve just as you enter Jeff City from the west on Highway 54, right at this Madison Street exit. The second project down the road about, I don't know, maybe 2 miles, was on Missouri 179 where it crosses 54. And this was more of a tangent section. You had a couple of locations where you were having some issues with rear end collisions right at this traffic light coming kind of down a little hill here. And again, at this point, and a little bit on the ramp coming off of 54 onto 179. The 2 Phelps County jobs, same kind of situation. These were interstate projects. This one is just a little sweeping curve around the Route J exit ramp. And then the second one was down on Route V. This is a longer project, and it involved treatment through the areas where we have had some incidents with people entering and exiting 44 from Route V. Now, the application method for high friction surfaces is fairly simple. There's a 2-part epoxy that is mixed on site, and it's applied in a couple of different ways. This is showing the application in the Route 54 location in Jeff City. The 2 components are mixed, and it's applied to the surface with a wand. You see over here. Next, once that's applied, it is evenly distributed over the surface using a notched squeegee to get everything in the consistent thickness. And then the chips are applied. In this case, this is bauxite. It's the ore from which aluminum is refined. And in this case, this is one of the methods for applying the chips. I can only describe this as kind of, if you've ever blown insulation in your attic, this is kind of the same principle. You know, high volume of air picks up these chips and blows them. You can see the guy has his hand over the end of the tube here, and he's using that to direct the chips down onto the epoxy surface. And it's important that the chips cover all the epoxy, but the depth isn't critical, because once it sets, those are going to be swept up, and anything that's loose is going to be taken away. The second method is a little more exotic. It's used more for longer sections. You have a single vehicle. Here you see the two tanks carrying the epoxy resins. It's mixed in a mixer here in the center, and then you have a bed that contains your chips, and it's all put down from this application bar in the back. The epoxy is sprayed down onto the surface immediately before the chips are dropped. And again, it's not terribly critical how thick they are, because whatever it doesn't embed in the epoxy is swept up. And you will see some here where you see a little bit of a gap where the guy's maybe not driving as close to that line as he could, but there'll be a couple of people following up the truck with buckets and shovels, and anything that's not covered will get covered by hand. Resulting surface it's a really nice looking surface. The chips are all about the same size, and it just makes a nice looking product once it's applied. As I said, the binder is all 2 component epoxy, and bauxite was the aggregate used in all of these projects. Bauxite, when you heat it, becomes very, very hard. It's on the Moore's hardness scale. A diamond is a 10, bauxite's a 9, so it's very, very hard aggregate. You get very little wear. The friction test was required within 7 days of application, and then another test was required within 14 days post-application. And there were some specs on what that post-application number had to be. Not sure. I don't remember what the minimum was, but it was always exceeded on these projects. The friction prior to the application was in the mid-30s. After the application, we were seeing numbers in the mid-80s, and it remained greater than 17 until the project was replaced about 6 years later. Now, excuse me, I'm talking specifically about the 54 Cole County location here, because that's the one we have the most information on. So prior to the application, I believe in the 3 years prior to application, there were right at 100 crashes. There were 32 the year before application. Post-application, we only had 1 year's data before the report was completed, but that had dropped to 5. And I can tell you that that's a conservative number, because I looked at the reports, and 2 of them actually, I believe from the description, occurred on the ramp prior to the application of the treatment, but they were logged to the main line by the reporting agency, so we had to use them there, even though I don't think that's where they occurred. And one of the other accidents was, I talked to the highway patrolman, and he said in that case the crash occurred when somebody went through that curve at over 100 miles an hour. So I'm not sure there's enough friction in the world to save you from that one. So as far as the cost is concerned, the way we approached this was to look at the National Safety Council estimates. They have estimates for the costs associated with each type of crash, whether it's fatal, disabling injury, or property damage. And we had the information from the types of crashes that were occurring at these locations. So when we looked at that, we came up with a weighted average cost of about $36,000 per crash. And when you look at the reduction of 27 crashes in that first year, the economic benefit calculates out to be more than $950,000, which was more than the total cost to apply the treatment at all 4 locations. So that's a pretty good return on your money. So once word kind of got out that this stuff was available and how well it worked, MoDOT started using it a lot more actively at different places around the state. It's kind of hard to tell on this map. It's a little fuzzy, but all the red dots are locations where the treatment was applied after that first project in 2013. At that point, Missouri decided that, well, let's see if we, now that we have some more information, let's see if we can do another project to analyze the safety before and after on these locations. That project was finalized out in 21. ARA was also the contractor on that. And the purpose was similar in some respects to the Highway for Life program. It was, is this effective where it's placed? Does it reduce track crashes? And is there a high benefit to doing so? It also threw in another factor, which is, could you come up with a safety performance factor to help guide the use in the future, where we weren't just doing it you know, based on hearsay or just a number where there was assumed to be a problem. The project that they gave us, there were 27 projects statewide, which turned out to be 67 locations. And I thought, oh, that's a lot of locations. That'll be a pretty good data set to work with. Then as we broke it down a little more, some of those locations had 2 or 3 segments in them. As they went around S-curves and whatnot, they would be broken into 2 or 3 segments. And so we ended up with 95 individual segments, which again, we think, oh, that's going to be good. That's going to be a lot of data. But then we started breaking down the segments by type. And we see first that 76 of them were on the main line, but 19 of them were on ramps. And ramps are troubling for a couple of reasons. First off, at that time, I believe it's changed now, but at that time, crashes were only reported or logged to the ramp, not to a location along a ramp. And in some cases, the entire ramp was treated, but in others, maybe only the first couple hundred feet where the ramp exited from main line or before it entered back onto a main line was treated. So anything that happened in between those 2 points was also thrown in the mix, so it made your data a little less accurate. Also, while 30 of them were undivided, 46 of them were divided. Those had to be looked at separately. And then 10 of the sections were tangent or straight sections, similar to that slide I showed you earlier on 179, where they may be in an urban section at a light or something like that. 66 of the locations were on curves. And just a little further breakdown, 18 of them were on interstates, 25 on U.S. routes, 17 Missouri routes, 15 RTs, and 1 business loop. For those of you who aren't familiar with the MoDOT system, they have 32,000 miles. These routes, especially the RTs, are probably in most states, these are county roads. So the variation in traffic between these interstates and these rural routes is pretty dramatic. So this slide is probably a little bit out of place, but we'll do it here anyway because that's where it is. When we've got the list, we started looking at it and we needed to verify the locations where the treatment was and get exact log miles and whatnot before we asked MoDOT to supply a lot of data for the analysis. So they have an automatic road analyzer, an ARAN. They've had them for years. I think they've had them since '87. I think they have 2 now. But again, for those of you that aren't familiar with it, it's a data collection vehicle that is part of their asset management program. They can collect rutting, they have roughness, IRI, all the geometric data is collected, video for processing, surface distress, that kind of thing. And for what we did here, a lot of what we used was the data from the camera that's sitting up here above the rear view mirror that gives you a right-of-way view of all the roads that they travel, and they collect all 32,000 miles every year. So they have a nice set of data to look at. The data that you get from that is available through what they call their data zone. When you open that product up, you'll get a map of the state, and you pick where you want to look at. So we had these locations and descriptions. We could zoom in to a specific location like this, for example. Here's your Madison Street exit off US 54. This is the curve that we talked about earlier. You go up here to the left and you click the little yellow truck, and by magic, here you are at the Madison Street exit. You can see the exact point the treatment starts. You drive down the road, see exactly where it stops. You can do that by year, and you can go back several years. I don't know how far back you can go on this, but it's several years. So if you want to go back and see what the condition of the road looked like before you applied the treatment, you can do that. In addition, some of the other data that we wanted to look at was available on this drop down. So all these little tabs have drop downs where you can select other types of data. And like for here, we've selected speed limit, so we can sort these out by speed limit, by surface type, get your traffic volumes, conditions, lots of information that's available to look at on these screens. In addition to that, through the miracle of Google Earth, we, as I said earlier, I think MoDOT doesn't have a friction truck, but ARA has a contract providing friction services for MoDOT, and we could take our GPS tags for the numbers and look at, again, here you can see exactly where the treatment starts, exactly where it ends. This is what I was talking about a while ago on this ramp, where it's only a portion of the ramp was treated, but here you can see where the treatment is applied the full length along the clover part of the clover leaf. So we were able to see exactly what we were looking at as far as the numbers were concerned. So once we had our limits all established and whatnot, we asked MoDOT to supply us with crash information, and we found 1,829 crashes that were identified within these project limits, both before and after the treatments were applied. We had all the detail on those as far as whether they were fatal, disabling, injuries, property damage only. And we also they've supplied all the data requested on roughness, rutting, cracking, curvature, super elevation, ADT, the whole shebang. This is where we were a little shaky here on the friction. There was very limited friction data prior to the application of the high friction surface treatments that we were looking at. Only 8 of the locations out of the 67 had data prior to application. So we used what we had, and that gave us a before estimate of about 35 on those locations, and an after estimate of about 78. So those numbers are pretty close to what you saw on the Highway for Life program. That one was a mid-30s before and a mid-80s, so it was a little bit higher. But I will say the average on the after was a little more variable when you had this many projects. We had a small sample that had multiple years of data prior and post, but we took what we had, and here's an example of a couple of the locations that we looked at. We were able to get a rough estimate of how long the friction lasts, and last is kind of a bad term too, because there's really no bottom cutoff for it. But we wanted to see what the average drop in friction number per year was. And using those curves on all the data we had available, we saw an average drop of about 4 points a year. So again, what's the life? Well, that's a tricky thing to say, but if we assume that starting point of 78 that we saw as an average, and you assume a 4-point drop a year, in 7 years, you're still over 50 or about 50. And I don't think anybody's going to argue that 50 is a pretty good number. And we assume the 7-year life because, in a lot of cases, that's probably the average life of your overlays. Some places longer, some places shorter, but if we use that for an average, we thought at that point something else is probably being done to the pavement regardless, because they're not, in most cases, they're not new when you put them down anyway. So, of the 1,829 crashes we saw, 1,425 were before, 404 after. So you saw a 72% reduction, but you have to be careful here because not all the projects were placed at the same time. Some of these you saw several years with the treatment in place, others less than a year. So that's a little bit misleading, but you'll see how in the future I'll show you how it's not that bad an assumption. The distribution, that's another nice part of the data set. We could look at the distribution between daylight and dark and the observed counts before and after, and you see a pretty good reduction both ways, but more of a reduction in daylight hours. Straight versus curved, again, you've got a lot more data here than you do on the straight sections, but again, you'll see a much greater reduction on curved sections. Dry versus wet, this is one of the biggies. The reduction on wet surfaces, as you would expect, was significantly better than on dry surfaces. So as far as the benefit cost analysis goes, we used the same method that we used in the Highway for Life program. We did a weighted average cost based on MoDOT cost factors and calculated based on the distribution of severity on each of the locations. We calculated an annual crash cost for each section, not overall, but for each one, and assumed a 7-year life. So of all the projects, these are all the jobs that were done, and some of these, again, had more than one location, but these are the jobs. You can see that for the most part, there were some pretty nice reductions after the application of the treatment. But you can also see that some locations had significantly higher number of crashes before the treatment than others. And some of these, where you get down in these areas, you had very few crashes to begin with. These would be some of those really low volume roads. So you see a reduction, and maybe that's a 50% reduction, but there's not that many crashes. So when you go into looking at your benefit cost, it's overall it makes things a little more complicated. Now, we've talked about the costs quite a bit, and I haven't really said much about how that was calculated, but these are the numbers that came from MoDOT that they used in their safety program, and they've assigned these values to different types of crashes based on national data. So you can see property damage only accidents don't cost too much compared to the more serious accidents. So again, you know, it depends on the location, but getting an extra one of these into your mix can make a big difference in your benefit cost ratio if you have a low number of crashes. And that's kind of what you see here. This is your benefit per year in millions. So some of those that you saw where you had a very high number of crashes, you get a pretty high benefit. Some of these where you had very few crashes in the first place, we actually saw a negative benefit. And that can be just the difference between, you know, throwing in one extra disabling injury or injury crash to the mix when you have a very low number in the first place. And I think we all realize that the difference between an injury crash or a disabling injury crash and a PDO may be nothing more than was the person in the vehicle wearing a seatbelt. I mean, one person not wearing a seatbelt that has a disabling injury on these low volumes can really throw your benefits into a mess. So the total cost on this of all the high friction surface treatments was about $4.6 million. Some of these were individual projects just to do high friction treatments. Some were done in conjunction with resurfacing and other types of projects, but pulling out just the cost, we came up with $4.6 million. The average return, or the benefit, turned out to be $35.6 million, which gives you about 114 benefit cost ratio, assuming a 7-year life. Once again, not a bad return. What you saw before, it's kind of spread all over the place, but that's the average. Now comes the fun part. Safety performance function. You know, this is kind of a way of using an estimate to analyze what kind of benefits you would have if you were to apply a certain treatment at a certain location. And the recommended procedures that Ashtel and Fawa use require large amounts of network data, and that just wasn't available for MoDOT. So we first looked at a generalized performance function and tried to understand the effects of friction as well as the other pavement roadway environmental factors. But again, we had limited data. You know, there's a lot of things that could affect these. There were a lot of things that were being done at the same time as some of the treatments. You know, other improvements, as we talked about earlier, like the addition of a shoulder or chevrons or rumble stripes, that kind of thing. So it made that a little more difficult as well. So we dropped down to a very simplified performance function that included all of the section data and had a limited number of variables. So based on the data we had and the general SPF, we basically used a ratio of before and after crash counts and segmented it by ADT, segment length, and speed limit. Friction wasn't included as an independent variable because we just didn't have enough before data to really do that in a way that made it meaningful. So we developed a generalized SPF for roadway and tangent sections. And you can see here on dry surfaces you get a benefit from the expected counts, but on wet surfaces you get a much more dramatic estimate of drop on wet surfaces. And if you use the numbers that we had from our averages from before and after, assuming all the other variables remain unchanged, we saw about a 73% reduction, expected reduction for wet weather crashes and a 24% reduction for dry crashes. This one, I'm not going to pretend to understand the statistics that go into this. We have very smart people that that did this part of the project, so I'm going to go into this in very little detail, but I'm just going to tell you that the empirical Bayes method was used to try to take out some of the unpredictable nature of the crashes, kind of like we talked about a while ago, where you know, you have some very low volumes, you have some very high volumes, and one or two crashes of a different type can really throw those counts out of whack. So this is kind of a way of doing a weighted mean for your data. If you look at some of these charts on your right, the little dots are the actual data observed. This blue line is what you estimated from the performance function, and then after you use the empirical Bayes methodology, you get something that's kind of in the middle. It kind of averages out those highs and lows, if you will. So the results come back to this. We were able to come up with ratios or percent reductions in crashes that were estimated based on what we saw in the data, and we see a 47% reduction on fatal crashes, 56% reduction in serious injury, 71 minor injury, and 57 PDOs overall. So again, when you look at that from a benefit cost ratio, and assuming that 7-year life, on all of these projects, your benefit cost ranged from a little over 2 to 409, with the average being about 60. And this is from the empirical Bayes method, where you take out some of those highs and lows. So what did we really learn from this? All the treated segments exhibited a high friction post-application, the average greater than 75. That's high. Again, you know, it's hard to say what is good and what is bad with friction, but I can tell you that when you get up in the 75 and 80 range like this, it's enough to pull the tread off your friction testing tires. That's good. I don't know that I've ever seen numbers higher than some of the numbers we saw in these projects. It's a very good surface. And if you look at the overall benefit cost, you know, you're doing very well. You're doing in the, you know, depending on which methodology you look at, from 60 to 114 on your benefit, which is again pretty good. And again, what you're really looking for is a reduction in fatalities. So that was over 50% there. In general, you're going to see a better reduction in wet-dry conditions and on curves than tangents, and that's to be expected. I think that's kind of common sense. But from your basic safety performance function, would indicate that you're going to see reductions in fatal crashes by about 47%, serious injury 56, minor injury 71, and PDOs of 57 in locations where you use this treatment. There wasn't enough data for a full safety performance function the way we'd really like to have done it. It just wasn't enough before data. But we think that the safety performance function can be used to identify locations to apply friction surface on an individual basis. So that's where we kind of stand. It would be nice to have more data where you could, and that's, of course, that's what we always say. Always nice to have more data, but at least this is something that can be used to estimate a benefit where you're planning on applying a treatment.
Okay, thank you, Jay. That was a great presentation, terrific delivery. We'll get to, we have received a number of questions we'll get to momentarily, but I wanted to share with the audience some of the upcoming webinars that we've got coming up in the next few months. On March 30th, we'll be speaking about probabilistic deterioration modeling for concrete culprits. Those of you who work on consideration of infrastructure deterioration know that that's a hot topic across the board. We'd love to know a lot more. As kind of Jay said, we always look for more data, but we don't have it. And then on April 27th, and you'll notice the diversification of topics as we go along here. I've mentioned this in previous webinars. We try to give you kind of a mixed bag of different topics because we have a very diverse audience who joins our program. On April 27th, we'll look at an old technology that's still a very valid technology, enhancing design through value engineering, and we've got two ARA speakers. To remind everybody, all of our speakers and presenters since the program began over now 3 years ago are all ARA subject matter experts. If you're interested in any of these programs or some of the future programs, you see you can register at ara.com/webinars. And currently we've got our program scheduled through July of 2022. Next slide, please. So Jay, just a few questions already received. Those of you who haven't submitted questions, we encourage you to do so. Please remember, if you're submitting questions now, submit them to both the panelist and to the presenter. So first question, Jay, is from Brian. And Brian's question, he wanted to know whether bauxite was a natural material or was a byproduct. And could you speak a little bit about the particle size? It appeared to him in the visual that the particles were quite small.
It is a natural product, but what they use is actually called calcined bauxite. They take the bauxite ore and they heat it to a high temperature. I don't remember the exact temperature, but that basically provides it a much harder material than before you heat treat it. The size is about 1/8 of an inch. I don't remember. I think it was 3 to 4 millimeters if my metric conversion isn't too far off. I think that's about 1/8 of an inch.
Okay, and we're still encouraging people to submit questions. We're getting quite a few. So Monica wanted to know, Jay, how well does this treatment stand up to heavy truck traffic?
Well, I don't know that we ever tried to break out the deterioration by trucks versus cars versus an average mix. I will just say that in every case that we applied it, the average drop was only about 4 points a year, and that's pretty good. A lot of these treatments were on interstates where you have a high truck volume. Interstate 44 is, gosh, like, I shouldn't say this because it's been a while since I've been at MoDOT, but I think it's running over 40% trucks, and the treatment held up fine. It was replaced on 44 because of some other issues and some other standard resurfacing projects, but I don't think we saw much of a drop difference regardless of where it was applied.
Okay, thank you. The next question is from Rasan, and this question is, what are the main causes of premature failure of this treatment? For example, is it less than 7 years? What would cause it to be less than 7 years?
Well, this is kind of outside the MoDOT experience. I'm just talking about what I've seen and what I've read. But the biggest issue with the failure of the surface is not the surface, but it's the condition of the underlying pavement. If you put this on this is not a treatment to use for rehabilitation. This is strictly for friction. So if you apply this to a pavement that has a lot of cracks, that it's rutted, for example, rutting is tough on this because you don't get your epoxy kind of sags, and you don't get a uniform treatment. If you don't have a clean surface where you don't get a good bond, that kind of thing. You can have delamination and that kind of thing. But I think the biggest issue is not with the surface. If you get the stuff stuck to a good pavement, it pretty much stays there. But I think I would guess that most of the failures you see are because it's placed somewhere where maybe it shouldn't have been. And again, I'm not saying that from the MoDOT perspective, because I haven't really seen a follow-up on this, but just from what I've seen in other publications, you can have some delamination in things if you don't do a good job of pre-selecting the site.
Okay, thanks again. And next question is from Ray, and Ray wants to know, is there a difference that has been able to be observed in the performance of this treatment depending on the method of application, i.e. mechanical or manual?
I don't know. I would think not, but I can't address that because the only sites that we were actually present on to see the application was the Highway for Life program, and the I-44 stuff was the automated, the 54 Cole County projects were basically the sprayed on application. I didn't see any difference in those, but of the 60 some locations that we studied in that second port, we weren't present, so I don't have any idea how those were applied. So I can't really speak to that.
Okay, the next question is from Jerry. What a great name, Jerry. And Jerry would like to know, is there a published report on the work that you presented in today's webinar?
No, the report is an in-house MoDOT report, and I don't believe it's been published.
Okay, thanks again. And we got about 5 more minutes for questions. We'll try and get to as many as possible. Another question from Ray. Was there different types of aggregate used between the locations that you showed, and were there noticeable differences in the performance of the surface treatment?
I believe that all the locations that we looked at were all bauxite. That would be, to me, be very interesting to see what other materials you could use and what kind of a number you could get. You know you're going to get that 80-ish number with bauxite. Is there another material out there that would get you mid-60s or something that would provide sufficient friction at half the cost? I don't know. That's something I'd really like to investigate. I was talking to somebody the other day about this, and they seem to think that one of the locations in Kansas City might have used a trap rock type aggregate, but when I look back through the data that we received from MoDOT, I did not see that listed. So if it was out there, it wasn't significantly different than the numbers we saw, or we just didn't see it, one or the other. I don't know. But in general, 99% of the stuff that they put down was all bauxite.
Okay. Next question is from Marina, and she would like to know. Very interesting. First, a comment. Very interesting to see the benefits you've shown, and a question. Have you looked from the number of vehicle passes where the surface treatment has shown tearing, I guess, unraveling or debonding, as I interpret that? And related question is, have you replaced the friction surface treatment where adhesion has diminished over time? And if so, how is that product removed?
That's going to have to be a question you're going to have to ask somebody at MoDOT, because I really don't know. We did the investigation on the surfaces that were in place. If they've had to replace any of them, I'm not aware of it, and the procedure that they would use, I'm also not aware of. I did say that they replaced the one in Cole County, but I don't think that there was an issue with the high friction treatment surface. I believe it was just part of another resurfacing contract, and then they replaced it after the fact. But I don't think there was an actual failure of the material. But I would have to refer you to MoDOT for some more information on that.
So, and we do have several questions that we won't have time to get to, but I've got a couple that I think are brief answers. We have a question from Lori, and could you speak to the surface preparation that's appropriate before the application of the epoxy?
It's fairly, as long as your surface is in pretty good shape, it's not a very in-depth prep. You basically sweep the surface to get any loose material off. I think the one in Jeff City that I remember, they had a compressor and they blew off dust off the surface just so that the epoxy would have a good bond, and that's pretty much it. If you have areas where you have a lot of cracking, and don't quote me on the number here, but I think it's above a quarter of an inch or something. The cracks are supposed to be pre-filled with epoxy before you squeegee down your total surface. But other than that, it's a pretty simple procedure. Not much prep.
Okay, thank you. And we do have a number of other questions that we don't have time remaining to get to. Jay has graciously, as we ask all of our presenters, provided his email address. He will be receptive to responding to the questions that we didn't get to, as well as supplemental questions that you might have during the next 24-hour period. He'll be responding to those. Can I have the next slide, please? So I want to thank everybody for joining today's presentation. As I mentioned at the beginning, we entitled all the participants who attended the entire full hour of today's webinar to receive a PDH certificate. That'll be accompanied by a PDF copy of today's presentation. And allow us, please, it takes us approximately 2 weeks to get the certificates prepared and transmitted. And if you have any questions, you can see the email address that is shown here. And I want to invite you back. We've got one more slide left, but remember, March the 30th, we'll be talking about deterioration models related to culverts of all different types of materials. Finally, for today, ARA is always looking for great people, as are many engineering and construction firms today. And we strive to get our valuable colleagues on our team. We sit at about 1,600 people, including our satellite offices of around 50-ish. And if you're interested in the current employment opportunities, you see the address where you can explore and submit a brief resume and your contact information. Once again, I want to thank you all and thank Jay for sharing his knowledge today. And God bless you all. Take care.